Okay, welcome to the fourth day of the week and the last lecture of Fabian Essler. And Fabian is going to talk, it's last pedagogical lecture of his. He's going to start talking about finite-size effects, which are small but important.
Yeah. Well, thank you, Sasha. I need the remote. Yeah. Okay. So this is as far as we got yesterday. And as Alexios already asked yesterday, so what about if my system isn't infinite, if it's finite? So then the story changes a little bit. And what I start with today is to discuss the physics of these finite-size effects. And then towards the second part of the lecture, I'll come to somewhat more technical or more advanced things that really have to do with integrability and what do you do if you have an interacting integrable model and you try to study quantum quenches in them. But let's start with these finite-size effects. Well, what if our system is finite? So then clearly local relaxation is impossible. Yeah? So that is clear because there's a Poincare recurrence theorem. If your system is very short, after some finite amount of time, which can be very short, the wave function has to come back to where it started. And only if your system becomes very large, this recurrence time basically diverges with system size, and you can forget about it. But now if I have a finite system, let's say 20 sites or 50 sites or 100 sites, there always will be some finite size effects, and these finite size effects, they preclude local relaxation because the infinite time limit doesn't make any sense. Yeah. So just, it's probably obvious to everybody, but just let me make that point. So if I have a ring and I shake things up, so information will start traveling around the ring. If the system is finite, the information after a finite time will get around and give me a finite size effect. In the thermodynamic limit, which I have discussed before, this cannot happen because you always do a local measurement. Yeah, so information can never travel around the ring and come back. Yeah, so these effects, and basically this idea that information cannot come back is essential for local relaxation to occur. Okay, so finite system, local relaxation is impossible. So that doesn't mean you can do nothing. So basically what it means, rather than having the nice situation where you shake your system, you wait, and then all local measurements become time independent. What you have to do for finite systems, you have to time average. And the quantities that can relax and typically do relax are time averages such as this. I mean, so basically what you do is you calculate or you measure some time-dependent expectation value. So this will remain time-dependent at all times. Okay, but now you just average it over some large time, capital T. So you integrate this time-dependent expectation value from 0 to t, you divide it by t, yeah? So that is the time average of this observable, and this quantity, if you wait long enough, typically does relax. Yeah? So for finite systems, the quantities that do relax are time averages. And how these time averages relate to the stationary state expectation values we discussed yesterday, I'll come to in a little bit. So that is one important point. The second important point is there are finite size effects in the dynamics, which you will see in any numerical experiment or actual experiment, which have no analog in the thermodynamic limit. They occur at finite times. Yeah, and you have to watch out for them, yeah, because they're not necessarily small. And if you're really interested in a thermodynamically large system, you basically have to stop your simulation at the times where the system finds out that it's finite. So I will discuss both of these in what follows. Okay, so let's first talk about the relaxation of these time averages. Yeah. Okay, so this is the finite time average as I have just defined it. O, once again, let's take it to be some local operator, yeah, for simplicity. Okay, so now let's expand this expectation value as we did already before in a basis of energy eigenstates. So H is the Hamiltonian that induces my time evolution. En are the energy eigenstates obtained from the time-independent Schrödinger equation. So now I can rewrite this time average by simply inserting a complete set of energy eigenstates here and here. So I get a double sum over energy eigenstates, some overlaps of the initial state with energy eigenstates, then a matrix element of the operator in energy eigenstates, some other overlap, and all the time dependencies in these factors here. Yeah? Now, that's a very complicated formula because these sums are obviously over exponentially many states, yeah, dimension of the Hilbert space. So this is not a very efficient representation for practical purposes. But now, in order to make progress, an assumption that is commonly made by people who study this eigenstate thermalization hypothesis and try to prove things or study finite systems, they basically make this assumption that the spectrum is non-degenerate of the Hamiltonian. So En is different from Em if N is different from M. Non-degenerate spectrum. That's just an assumption. It's not generically true. Usually you have some degeneracies, but there will be few of them. So the argument basically is let's forget about that. So then you always have a non-zero contribution here in Em minus En unless M is equal to N. But for all other terms, now you do this integral, yeah, and if capital T becomes large enough, the off-diagonal terms, when N is not equal to M, yeah, they will be suppressed like 1 over time. So in the late time limit, so averaging over longer and longer time periods, all the off-diagonal terms in this double sum will disappear, and the double sum will reduce to a single sum. Yeah? That's just elementary, just doing this integral. So in the late time limit, so t goes to infinity, this time average, therefore, is a single sum over energy eigenstates, some overlap, amplitude squared, times expectation value of your operator in all energy eigenstates, and this right-hand side is called diagonal ensemble. Sasha.
The question is the following, that when you're doing this, you assume that it's finite system, because suppose that there are EM and EN are very close.
No, finite.
Many of them.
So now I keep the size fixed.
So time goes to infinity before size.
Absolutely. I mean, so this is a crazy stuff from that point of view, right? Because so you keep the system finite, 50 sites, but you take the time goes to infinity. That basically means information travels around your ring infinitely many times.
The space to be finite, or just the spectrum to be discrete? Because
spectrum to be discrete for this simple argument to work.
But you don't want n to be finite. It can go to infinity.
In principle, yes, yeah. I think
that's the difference between, say, a particle in a box,
no, I understand,
or
but,
spins.
I mean, this is supposedly general. Yeah.
Okay.
So, and this assumption, which we make in order to be able to do a calculation, is believed, but that's all it is, to not be necessary. So the belief actually is that this diagonal ensemble describes the steady state basically for any system. Yeah. And it's called diagonal ensemble because it only involves expectation values, so diagonal terms, of your operator in energy eigenstates. Okay?
The system is finite. It can have a large number of species, like large N theories and so on, in which the level spacing can again go down. With so then this t going to infinity would have to mean that t is much larger than some quantity
That's correct.
related to n.
Yes. in order for this simple argument to have some validity. Yeah, but so basically, what people say who do this kind of stuff, so that's not me, they basically say well, most systems you have some degeneracies, but they're few. Yeah, and as long as the degeneracies are few in some sense that needs to be sharpened, this will still hold. You still can reduce this to this in the late time limit. Yeah. But if you want to prove something, you basically have to make this assumption. Yeah. Excuse me? MBL. Well,
what have you assumed more than?
No. So here, I haven't assumed anything in a sense. I mean, so this argument is completely general. So as long as you don't have degeneracies in your energy spectrum, yeah, so the level spacing, if you wish, is finite, this will always go through. Yeah, so the only thing I have assumed on this slide is I have no degeneracies, and because I take time goes to infinity in the end of the day, but I want my level spacing to be some fixed scale. Yeah. So then you get this diagonal ensemble, and what this diagonal ensemble means, of course, depends on your system. Just to be clear, this is a very complicated formula. It's a sum over all energy eigenstates. So we have exponentially many states here. Okay. And so now let me carry on. Now let's try to connect this to our subsystem relaxation that we discussed before, because what I will argue now is that the two are in fact, for systems that do relax, very closely related. So, now it's believed that for local observables, this infinite time average I just discussed, up to finite size corrections, is in fact the same as the corresponding expectation value of the same operator calculated in the framework of this local relaxation. Yeah, where the system is infinitely large and you don't have to time average. Yeah, so they are not the same. You can check this, I mean, for specific examples, but the difference always goes away when the system size becomes larger and larger and larger. Yeah? Once again, there's no proof of this statement, but you can investigate this for examples, and it seems to always work out, and it's a reasonable assumption to make. Okay? So in that sense, this time average relaxation and the local relaxation that we have discussed before are related. Now, that at first sight, and now I talk a little bit about eigenstate thermalization or aspects of eigenstate thermalization somebody asked about, Sriram I think asked about yesterday. So now that's strange, yeah? Because if this is true, and I've just asserted, of course without proof, that it is true, the diagonal ensemble must be able to describe thermal states. Obviously, yeah, because some systems, as I argued, thermalize. Now, that's weird. Why is that weird? Okay, so if you look at your infinite time average, your diagonal ensemble, it encodes an enormous amount of information about the initial state. All of these overlaps actually enter. Whereas the thermal density matrix only knows about energy. That's the only information about the initial state the thermal density matrix remembers. How can the two be the same? I mean, that's weird. Yeah? And the answer to that is, well, there's something very profound going on with eigenstates of local Hamiltonians, and there is some kind of theory, if you wish, behind this, which is known as eigenstate thermalization hypothesis. And I'll discuss some elements of this in the following. Now, in order to show that this diagonal ensemble can be equivalent to a thermal ensemble, we need a few ingredients. So essentially two main ingredients. One ingredient is, as we said earlier, expectation values of local operators in eigenstates of local Hamiltonians, and a local Hamiltonian is one where the density is a local operator, so short-range interactions, etc. We said earlier that diagonal elements in the energy eigenbasis of local operators up to finite size corrections actually can be taken in any energy eigenstate in a micro-canonical shell. Yeah, so that's basically what that means. It means if you have a generic Hamiltonian which doesn't have any conservation laws other than energy, so you diagonalize that Hamiltonian in your mind, so to speak, because in practice, of course, it's difficult to do. So then at a given energy or energy density, now you pick out your favorite energy eigenstate, you calculate the expectation value of some local observable, you get some number. Now you just pick a very close by an energy eigenstate, calculate the same expectation value, and the results will be the same up to exponential corrections. So it basically means all of these eigenstates at that energy density locally in space are thermal. Yeah? And that's a quite profound property of eigenstates of local Hamiltonians. Yeah? So that's the first ingredient. Now the second ingredient, and I'll give the calculation on the next slide, for large system sizes, these overlaps here are strongly peaked in energy. Yeah? So let me show what I mean by this. So, as I said, the Hamiltonian, for any of these arguments to bite, has to be local, so it has to be the sum over local operators, short-range interactions only. Okay, so then we work at some finite energy density now, so the average energy is just the expectation value of the Hamiltonian in the state you consider. So this is the initial state, and what I want to do now is I want to estimate the variance of the energy in that state. Yeah? And the variance is simply defined as the expectation value of the Hamiltonian squared minus the expectation of the value of the Hamiltonian bracket squared. So that's the variance in energy. So in other words, at that energy density, if you wish, so the probability distribution of energy will be some Gaussian or something like this for large system size. And what I do now is I calculate basically the variance of the probability distribution. Okay, so the right-hand side here, you can rewrite basically just using that the Hamiltonian is a sum over local terms. So you can rewrite the right-hand side as a sum. Yeah, so you basically replace H just by this, of connected correlators. And it's connected correlators of the Hamiltonian density. And now what you use is that these connected correlators, because your state is supposed to have what's called cluster decomposition, basically vanishes for large spatial separations. Yeah. So this is a requirement we basically put on all of our initial states. So they have clustering properties. So that basically means if you look at connected two-point functions of local operators in these initial states, if you take the separation to infinity, then the connected correlator has to vanish. So this is something you always require in StatMech type of problems. Yeah. So this vanishes, and then this the mere fact that it vanishes tells you that the variance, in the worst possible case, can be a power law in system size, L to the alpha, but alpha is necessarily less than 2. Yeah, because in order to get L squared, this connected correlator actually would have to go to a constant at infinity. at infinity, not at infinity, at system size. Yeah, so just remember it's a finite system of size L. Yeah. Okay, so the variance is bounded by a system size dependence which goes L to the alpha, where alpha is less than 2, but the energy itself is extensive, so the energy scales with L. So the variance over the expectation value of energy squared actually scales like L to the alpha minus 2, so that goes to 0 when L goes to infinity. Yeah? So this is basically tells you that these overlaps are strongly peaked in energy. Yeah? So they have tails, but basically if the system size becomes large enough, the probability distribution is strongly peaked. So now I use this, go back to my diagonal ensemble. So I have property 1, I have property 2. So now I can use this by basically, first of all, saying these are strongly peaked in energy. Yeah. So then what I can do is I can focus on the window in energy where the probability distribution is strongly peaked. Yeah. In that window, all of these expectation value, the diagonal elements are the same by property 1. So I can pull that out of my sum. And then I'm left just with the sum over n over this overlap matrix element squared. But this just sums up to 1. Just the normalization of the initial state. And this then tells you that the infinite time limit of this time average goes to the micro-canonical average. And that's what I wanted to show. Yeah, so this diagonal ensemble, although at first sight it looks like it encodes an enormous amount of information about the initial state, it doesn't have to. Yeah? So for systems that thermalize, the diagonal ensemble simply becomes equal to the micro-canonical ensemble. Similarly, if you have an integral model, if you have conservation laws, you can repeat this kind of argument, and then the diagonal ensemble reduces to the generalized Gibbs ensemble or the generalized micro-canonical ensemble, modulo finite size correction. So note that I needed here that my system size was large, yeah, because only then the probability distribution of energy became peaked. Yeah, but that's okay because for finite size corrections to be small, I need the system size to be large. Yes, I'll come to that. So there, it's an integrable model, rational conformal. These are integral models, rational conformal field theories, and they're actually not just integrable, they are what I would call super integrable. In some sense, I'll come to a little bit later. So in rational conformal field theories, finite size effects can be particularly pronounced. And I'll just give me 10 minutes. I'll come to that, and let's come back to the question then, perhaps. Yeah. So because rational conformal field theories have a very commensurate spectrum, and when you have a commensurate spectrum, the types of things I talk about next occur. Yeah. So you're happy with diagonal ensemble, okay? So then we carry on. So now let's come to other finite size effects, which I call traversals and revivals. So revivals or recurrences is something Alexios was asking about yesterday. Traversals is something else. So now let's come back to our previous example, which is this tight binding model and the initial state, which was just this product state, this charge density wave, where we had one particle on every other side. Okay, so now let me compare the time evolution after this quantum quench in the infinite system to the time evolution in a finite system. Finite system, I take a ring with 64 sides. Yeah. You can also look at an open box. I mean, life's too short. I just look at a ring, yeah, because I'm just interested in finite size effects per se. So in the infinite volume, so if I look at the connected density-density correlator, I have this light cone effect, which we discussed yesterday. So this, or an equivalent plot to this, I showed you yesterday. So now on the 64-side ring, you see the connected density correlation function looks very different. So at short times, yeah, so in this regime here, well, they look pretty similar. Yeah? But then after some time of about jt is equal to 8, this starts looking very, very different. So there's a very strong, pronounced finite size effect, which I call a traversal. And it will become clear in a moment what I mean, why I call it a traversal. So basically what happens is this light cone, it propagates, yeah, so it kind of spreads, and at this time, it goes around the ring. So it traverses the ring. That's why I call this a traversal. And so this is a finite size effect you always have in basically any theory. Yeah, integrable, non-integrable, whatever. So these finite size effects like traversals, completely generic. So now let's see. Yeah, so here, if you now measure the connected density correlator at a given separation. So you fix the distance between your two density operators, yeah, and you ask, what does the connected density correlation function look like? Well, so initially, it's basically 0. Then at some time, which I call TL star, the light cone first hits, yeah, that point, and you start having a signal. So this is what we discussed yesterday. Yeah, so this is the time at which you basically start seeing a sizable connected relation. Okay, but so now, if you now wait longer, you see eventually at some time, which you can work out is this one here, which contains the system size, the reflected light cone or the traversed light cone returns. Yeah, and you get another signal. So basically, what happens is, so this light cone hits the boundary of the system and then moves here, and this one hits the system size here and then comes back here, and so you see, you basically have a big peak here, then you have some response, and then you have a second peak, a third peak, and so on and so forth. So now, if you are, do I have a plot of this? No. So now, if you are, if you're very naive, you might think, okay, so here I have my observable, so O j of t, Oj plus L of t, and here I plot t. Yeah, and then the way it looks, you have something very small, so then you have some signal, something happens here. Then you have another peak, yeah, and then something else happens, and you have another peak. So this is what it actually looks like in this cut. So now you might say, well, okay, so this could be a recurrence or a revival. Yeah, so the state of the system comes essentially back to where it started. Yeah, you might think that. And what I'm going to show you now, this is not at all what happens here. Yeah? So this traversal is a very simple effect, which is basically just the light that moves around the system, has nothing at all to do whatever with a revival or a recurrence. Okay, so what is actually a recurrence or a revival? So that's a very different phenomenon. So this traversal is a generic finite size effect. You see it in any numerical simulation, blah, blah, blah. And if you want to do a numerical simulation, which you in the end want to compare to something calculated in the thermodynamic limit, you always have to stop your simulation here. You must not go to later times, because otherwise you analyze finite size effects. Okay, what's a revival? Okay, so revival is defined in terms of the return amplitude. So that is the probability of the wave function of the system, or the state of the system, to come back to where it was initially. And a recurrence would be, this return amplitude is 1. Okay, but if in quantum mechanics, if you have one of these spin systems with 20 sides or whatever, the time before this happens is probably a few times the age of the universe or something like that. So you can forget about that. So recurrences are not important because you can never really observe that in a finite time. So you weaken this requirement and say, well, rather than the wave function coming completely back to where it was within epsilon, let's just require that the state comes back to where it was approximately. So let's say I call a revival, a situation when the state of the system has an overlap with the initial state, which is order 1. It could be a half, it could be a tenth, it could be a 20th if you wish. I call that order 1. And yeah, okay, so you could, I haven't considered that. Okay, so you could investigate that. So I just have considered where this is order 1. And this is a very strong requirement because basically, as your system size grows, as I'll show you in a moment, so this overlap generically is absolutely tiny. Yeah, so there's a very strong requirement. So, yeah. Yeah, so the fringes is basically what I have shown here. So this is part of the dephasing of the two-point function. So this is a two-point function. So here, this is the light cone effect. You're very small here, exponentially small, but then you start having a peak. And after that, you typically have some oscillations in the two-point function. You also have that in the infinite volume limit. Yeah. So the fringes are basically okay. So they're compatible with the thermodynamic result. But this peak and so on are not. Yeah, and these are the traversals. Yeah. So now let me talk about the revivals. So here I've worked out for you for a 64-side system, for exactly the model I'm discussing, tight binding model with the initial state, I've worked out what the return amplitude is. So this is 10 to the minus 4 times the return amplitude. Yeah. And you see, it's basically 0 in the time interval I've plotted here. So I went up to jt equals 14. Yeah, and this traversal happened at jt equals 8. And there you see the return amplitude is literally 0. I mean, it's absolutely negligible. Yeah. And then you start having a little bit, a tiny little bit, well, it's not really a revival in the sense I've defined it, but so here you have a little bit of a revival-ish feature, and here a bigger one. But return amplitude throughout is really, really tiny. So that tells you this traversal has nothing to do with a revival. Yeah? So the state itself doesn't really come back to where it was. The state is very different at these times where the light cone has moved around. Now let's come to CFTs or systems with commensurate spectra. So revivals, which I've defined here, have a very different origin. Yeah? So the origin of the traversal is literally just information spreading around the circle and coming back. This is a simple property of spreading. Revivals are related to regularities in the spectrum of the Hamiltonian. Yeah? And a particularly nice set of examples of that fact was worked out by John Carty in 2014. He considered rational conformal field theories, which are really the prime examples of theories with commensurate spectra. So let's try to understand this fact in simple terms without having to discuss CFTs. So why are revivals related to regularities in the spectrum of H? So once again, let's rewrite the return amplitude in terms of a basis of energy eigenstates. In terms of a basis of energy eigenstates, I can rewrite it like this. Yeah? Obviously. And so the time dependence just enters through these factors here. Yeah? So which is the energy eigenvalues times t. So now, imagine that your Hamiltonian has a commensurate spectrum. Yeah? So in the simplest case, it could be like a harmonic oscillator. So these ENs are proportional to N. That's perfect commensuration. It's an equally spaced spectrum. So then there will be times, yeah, a sequence of times where all En times t are multiples of 2 pi. So these phases go away. All of these phases are 1. Yeah, these phase factors are 1. And then the return amplitude actually becomes 1, and you have a recurrence. Okay? So basically, if you have now a commensurate spectrum, so that means the energy eigenvalues are not equally spaced, but they have a very regular structure, then you can always find times t star, so that for all energies, energy eigenvalues, En times t star is approximately 0 mod 2 pi, and in these cases, the return amplitude will become approximately equal to 1, and you will have a revival. Okay? So that's what a revival is about. It has to do with commensurations in the spectrum of the Hamiltonian. So now a simple example I've worked out for you here is, let's take our tight binding model, but now let's make the hopping long range. Yeah? So basically I allow hopping between faraway sites, but the amplitude of that decays in this particular power law fashion. Now, why have I done this? Well, I've done it because if I look at the spectrum of this Hamiltonian, which I can just work out by going to Fourier space, you see this, the dispersion relation is approximately linear. Yeah? And of course, if you have an approximately linear dispersion, the spectrum will be commensurate in a finite size system as you have here, because in a finite size free theory, so the momenta are just 2 pi n over L, yeah? And now if you have epsilon of Pn is to a good approximation some velocity times Pn, yeah? Then you basically see that this is 2 pi v over L times n. So you have approximately an equally spaced spectrum. Yeah? And spectrum looks like this, approximately linear. And now I have once again worked out for you what the return amplitude is. And now look, there is no rescaling here. So this is really a scale from 0 to 1. And you see at some time jt equals 20, you start having a revival. Okay? And conformal field theory is basically some complicated version of what happens here. And not just complicated, there's a lot more structure. It's very, very interesting. Very intricate structure that emerges. And if you want to learn about this, you can look at John Carter's paper. Now, these revivals are not just a theoretical concept. So they have been observed in some experiments. And in particular, there was an experiment in Jörg Schmidtmeyer's group in Vienna last year, which is a variant of this experiment I started my first lecture with, yeah, this split Bose-Einstein condensates. And what they do after the dust settles, let's say, so you need to basically develop a theory for the measurements, etc., which was done. What they measure is basically a connected two-point correlation function of some phase field, yeah? And this phase field is described by a free relativistic boson in 1+1 dimensions, and so they measure this two-point function, and they then do a very careful analysis of that two-point function. So what they see is this is the correlation function as a function of time, and what you see is you see a bunch of signals, and they did a careful analysis to rule out that these are traversals. So these indeed seem to be revivals in this case. How is that possible? you might say, because I just told you, well, it's related to regularities in the spectrum, it's very difficult to see. Well, a free relativistic boson in one dimension is a conformal field series, so it has a linear dispersion. Yeah? So it has a dispersion which basically looks like this. The system is finite size, so there you basically have a chance to see something like that, and they do. Yeah, so what they observe here is a revival in a particular correlation function. So the statement is, thank you for making that comment. So the return amplitude itself, of course, you can't measure. Yeah, I mean, so what is measured in the experiment usually is some correlation function. Yeah. So now, if you have a revival, basically any correlation function would have to exhibit a revival, because the state comes back to where it is itself. And so the correlation function they have access to shows this structure, yeah, and they can rule out that this has anything to do with traversal. And there's more to this. So the free boson is a free theory. So we have a Wick's theorem. Yeah. So if you see the revival in the two-point function of vertex operators, you basically will have to see it in all higher point correlation functions as well. So if you buy all that stuff and take it into consideration, this is quite a strong result. Yeah. Yeah, so I asked them the same questions, and they looked into size dependence of these quantities as well. So it's in their paper. It was a science paper, appeared, I think, earlier this year. I think so, yeah. No, I mean, I could give a few lectures on this. So this is a very interesting set of experiments, as a matter of fact. So it's a system of interacting bosons, rubidium atoms. Yeah. But the measurements or the regime they access is a low energy regime. Yeah. So you basically start with your linear model, you do some quantum quench, but the energy regime that is accessed is low energies. And at low energies, the linear model reduces to a low energy effective field theory you can derive by bosonization, and that's the free boson. So you could ask, what about curvature effects, etc. But okay, I mean, so the theoretical analysis that has been done for any of these experiments is basically done in the framework of Langer liquid theory. Yeah, and that's a conformal field theory, etc. And this kind of rationalizes why they see what they see. And of course, there will be deviations, and it would be interesting to quantify, etc. But the subject is not at that level at the moment. Yeah. Okay, that's all I wanted to say about finite size effects. So here are some more exercises for those of you who want to do lots of exercises. But okay, let's maybe move on. So you can look at them on the website later if you're interested. Now, so far, I basically just have given you qualitative pictures of the world of quenches. And I haven't really gotten to the integrable part of the whole story, right? I mean, so free theories, it's all very well. So I've used free theories mainly because you can understand the phenomenology by just looking at free theories. Now, I'm not in the business of kind of like solving free theories. Really what we want to do is we want to study interacting integrable models. Yeah? So now you want to basically look at quantum quenches in interacting integrable models, and you want to basically understand relaxation in these interacting integral models. You want to describe the steady state, then you want to describe the time evolution, all this stuff. Yeah, and that's hard. But so this is basically what we have been working on the last so many years, and there's a significant amount of progress. And what I will do, what I will attempt to do now in the remaining 45 minutes, I just try to give you a flavor of the ingredients, yeah, because in the end of the day, as always with integrable things, the calculations become very technical, yeah, and this wouldn't be appropriate for a lecture at a school, so I will give you a flavor, and if you want to know more, I can maybe say some things about more technical details in the discussion sessions this afternoon, or you can talk to me in private. So now, after this prelude, what I will do for you, I will once again discuss something in free theories, yeah, contrary to what I have just been on about, but I will basically discuss the steps we have gone through for the interacting integral case, first for the free theory, because the ingredients are the same. Yeah? And if you understand this, then you understand what you have to do for the integral model. And then I tell you a little bit what the analogous quantities that we need, and which are easy to understand for the free theory, are for the integral model. And I give you a crash course in 30 minutes about Bethe-Ansatz, thermodynamic Bethe-Ansatz, etc. And then the details, Fabio will fill you in his lectures, I hope. So let's see how it goes. Okay, so now the key objects in all of this analysis are two. Macrostates. We don't want to work really with microstates. We want to work with macrostates. And conservation laws. Yeah? And both of these are common, let's say, in free theories, integral theories. And what I will do now is I will first discuss it for the free theory. So our favorite model is this tight binding model, which we have been talking about, Hamiltonian momentum space. Okay, so energy eigenstates, I can really simply write down in the occupation number representation. So these are the occupation numbers of the different momentum states. The occupation numbers are either 0 or 1 because I deal with fermions. Yeah, and this is just a Fock state in momentum space. The Fock states are all eigenstates because energy eigenstates because it's a free theory. Yeah, and the eigenvalues I can just obtain from here. Okay. Now, clearly, as you can just read off from this form of the Hamiltonian, the mode occupation numbers, n hat of k, which is a c dagger of k, ck, are conserved quantities. They commute with the Hamiltonian, they commute with one another. Yeah? And one more thing, I mean, so these n-particle eigenstates I can characterize by n integer numbers, which I call ij, which are related to the momenta, which are occupied in my Fock state. Okay, so all of this you know. Now, the mode occupation numbers, that is a concept which does not generalize to the interacting integral case. So you have these simple modes only for free theories. In interacting theories, it's replaced by something which is considerably more complicated, which I will discuss next. So what's therefore important is rather than working with mode occupation numbers, we should work with local conservation laws, in the sense that I have defined in my first lecture, the densities of these conservation laws should be local. I can easily construct these for the tight binding model. Here they are. Yeah, so these operators here, so it's basically just hopping terms, but not between neighboring sites, but between next nearest neighbor, next nearest neighbors, and so on. Yeah, so I can rewrite them in momentum space. In momentum space, they just look like this. Yeah, and this immediately tells you these conservation laws, because they can be expressed entirely in terms of mode occupation operators, they will also be conserved. Now, they are local in my definition. They're conserved. Yeah? And there's a second family which, instead of the plus sign, I have the minus sign. Then in order to get a Hermitian operator, I have to put an I. And then in momentum space, instead of a cosine nk, I have a sine nk. So there is two family of mutually commuting local integrals of motion. Yeah, the Hamiltonian is a particular example. Yeah. This notion of having mutually commuting local integrals of motion, that generalizes to the interacting case. This we will generalize. Now, in the free case, I can go back and forth between mode occupations and these local integrals of motion, so the inversion formula is just written here. Yeah? So for free theories, I can work either with these local integrals of motion or with the mode occupation numbers. The latter is usually more convenient, so a lot of people do this, but you can equally well work with this, and this is the concept that generalizes. Okay, what about macro states in free theories? So this, all of you know, you learned about this in your StatMech courses, but let me briefly recap it because it sets up the formalism that I need in the interacting case. So we're interested in the thermodynamic limit, which is the infinite volume limit at fixed density. Starting point are energy eigenstates for large, asymptotically large finite volume. So in these, as I've just discussed, are Fock states in momentum space. Okay, so now what we want to do is we want to define a mode occupation density in the thermodynamic limit by coarse graining. Yeah, and we do this very easily by basically saying this expression here defines a function n of k in this limit. I say n of k times L delta k of 2 pi is the number of occupied momenta in the interval k plus delta k. Yeah, so that basically tells me in the states I consider how many momentum states are occupied in some momentum interval delta k. Okay, so in the thermodynamic limit, so this just becomes a function of momentum, and each function, positive function that takes values between 0 and 1, such that the integral over all momenta of n of k is equal to the density that I keep fixed in the thermodynamic limit, defines a macro state. Okay, so these are the sets of macro states. So this is all the information that you need to do thermodynamic. Now, different macro states are fixed by fixing conservation laws. So what I mean by that, so if I have a macro state, which I call rho now, so that means I specify some function rho of k, which is one of these mode occupation densities. I can very easily calculate, it's an elementary calculation, as you can see, the expectation value of the local conservation laws in that macro state, because in fact, the macro state arises from eigenstates of these higher conservation laws, because they can be expressed entirely in terms of the mode occupation operators. So this expectation value is simply given by this formula here, where these are defined here. Yeah? Which are the generalized energies of these conservation laws. Yeah? And so basically now what I say is by fixing all of these numbers, I uniquely specify rho of k, so to speak. And so I pick out one macro state. And that's the basic principle I will use to construct my steady state density matrix. Yeah, so if I can fix all of these conservation laws by calculating the expectation value in the initial state of a quantum quench, it gives me these numbers. Yeah? And then in the steady state, I want to construct the generalized micro-canonical ensemble. So I want to basically fix now an energy eigenstate or corresponding macro state. And I can always reconstruct this macro state once I know these numbers by inverting this formula. So that is the idea. Yes. Yes. So this was the inversion formula. So clearly the i's are related to the n's because that's the right-hand side of the formula. So I can express the i's in terms of the n's, and this expresses the n's in terms of the i's. Yeah. So they're equivalent in this case. And so for free series, you go back and forth, and that makes things easy. For the interacting case, you can't do that. Yeah. So you really have to work with the i's. Okay, so let's see. Now, an important point is expectation values of local operators can be reconstructed by just knowing thermodynamic information, so the macro state. So this is shown here. So let me consider a macro state characterized by some mode occupation density. Okay, so then it's easy to see all local correlators depend only on this function up to finite size corrections. So what that means is, now let me calculate the expectation value of some local operator. So here just C∪J CL at some fixed difference in some Fock state. Yeah, and that Fock state basically in the thermodynamic limit, so to speak, reduces to this macro state. Yeah, so the full answer, you can just calculate what this is. It's an elementary calculation. Is this sum? Yeah, and Nm is either 0 or 1, depending on whether that momentum state is occupied or unoccupied here. Okay, so now in the thermodynamic limit, when L becomes large, I simply turn this sum into an integral. Yeah, and a simple calculation then gives you the right-hand side is just an integral over e to the I k j minus L times this mode occupation density plus terms which disappear when L goes to infinity. Okay, so basically, in order to calculate local observables to order 1, I only need to know this n of k. And that's important. That's exactly what I want to do in my steady state density matrix. And that's important so because it tells you you don't need really microscopic information. Macroscopic information is sufficient. Yeah, so if I can work out what is n of k, yeah, for my generalized micro-canonical ensemble, I'm done. Secondly, and we had a question about this already in the first lecture, local correlators are most affected by the most local conservation laws. So somebody asked, well, do I really need this infinite number of conservation laws if I just want to describe nearest neighbor correlators? And the answer is, well, in this particular example we look here, absolutely not. Because if you look at this quantity, which is the one we're interested in, you can express it in terms of initial data, so expectation value of local conservation laws in the initial state. And it only involves conservation laws where the density basically fits into the interval that is described by the separation or by the size, by the extent of the local observable you consider. Yeah? And now, in the particular example, it looks very special, and it is very special, but you can show, and we did this a few years ago, so this idea actually generalizes. So if you want to describe a very small subsystem, what's very important is only the conservation laws which have densities which are of order the extent of the density is of the same order as the subsystem size you're trying to describe. And that's very important. Yeah. Yes. Yeah, in this particular example. I mean, so look, it's a very simple example. So this is, of course, too simple, but it generalizes. So typically what you find, we did this for transverse field easing, it's quite complicated. So there, all of the conservation laws contribute substantially up to those where the density basically covers the subsystem plus one correlation length on either side. No. So of course not. But to show subsystem thermalization in interacting integral modes, of course you have to look at more than the two-point function. So you cannot use Wick's theorem to elevate it. Absolutely not. Yeah. So Wick's theorem is just in the non-interacting case. Okay. So now come back to quenches. So I discussed a little bit now just macrostates in free theories and their relation to integrals of motion. Now, what about what we really want to do is describe or construct a generalized micro-canonical ensemble describing the steady state in a free theory after a quantum quench. Okay, so you can do this as follows. So you fix a macro state described by some mode occupation density rho of k by simply requiring that the expectation value of these integrals of motion, these local integrals of motion, in the macro state, which is the right-hand side, equals the expectation value of the integral of motion in the initial state, which is the initial data. So that's a necessary condition, yeah, for this macro state describing the generalized micro-canonical ensemble. And this uniquely, for the free theory, this uniquely picks out a function rho of k. Okay? Once I have this function rho of k, then I extract from the macro state now a particular microstate which corresponds to the macro state in the infinite volume limit. So you can go back now to an asymptotically large finite volume. And having the state which I call a representative state, so it's just one state, pick microstate from the basin of attraction of the macro state. And you form this one-dimensional projector, and that is your steady state density matrix. And you can prove that this gives a correct description of the steady state. Okay, so this is how things work for free theories. Yeah. Do you have any questions about this?
Any choice of phi will do.
Sorry?
Any choice of this pure state will do.
Yes, and because of this property here, all local correlators depend only on the macro state up to finite size correction. So if I change the micro state, I only pick up finite size corrections, but I take, in the end, after the calculation, I take the infinite volume limit, so they go away. So therefore, every microstate gives you the same answer. Yeah, so the choice of representative state is up to you. I suppose in the free case, the answer is yes. In the free case, it's obvious. But you see, in the interacting case, I don't want to answer. I know the answer to the question, but I don't want to give it. So the problem is the following. So for the free case, you can do what you say, yeah, because modes are absolute. And in the interacting case, this doesn't generalize. You can't do this. So in the interacting case, the best you can do is you can work with thermodynamic information. So these mode occupation densities. Yeah, so, and finite size corrections you don't control. They're way too complicated. So in order to do what you want, you basically would need to know the exact answer. Yeah, exactly. And what you would want to do in principle is possible, in practice absolutely not. Yeah, and so what we do is we work only with thermodynamic information, and then by construction you focus on macro states. Yeah. Okay. Well, one more thing very quickly. Well, okay, so we'll see how it goes. Let me remind you of the counting of the number of microstates in a large finite volume that corresponds to the same macrostate. So here I have my mode occupation density n of k. So here's my Brio zone 0 to 2k. Yeah. And now you want to calculate how many microstates reduce to this macrostate if I have an asymptotically large volume. And basically what you do is, okay, so you first look at the number of vacancies, so momentum states in this interval of momenta, yeah, and the number of vacancies is simply delta k, which is the size of the interval, times L over 2 pi, which is the spacing, which is 1 over the spacing between adjacent momenta. So that's the number of momentum states in that interval delta k. And the number of particles in the same interval is simply obtained by multiplying this number of vacancies by n of k. N of k is always between 0 and 1, so there's a smaller number. Okay, so now what you can do is, without changing the macrostate, you basically can distribute these particles amongst these vacancies in any way you want, yeah, because all of these microstates correspond to the same mode occupation density, so to the same macrostate. So the number of ways of distributing n particles among n and vac vacancies is simply given by the binomial distribution. Yeah? And for this little interval, that contributes a factor which is given here. And I write this now as the exponential of delta S. Delta S is the contribution to the thermodynamic entropy. And once you work it out, so now you use that L is very, very large. So these numbers, delta N vac and P, are large. So you can calculate these factorials using Stirling's approximation. So then delta S is given by this formula here. And that, I hope you recognize as the expression of the density of the thermodynamic entropy for the free Fermi gas. Okay? Now, the message, why do I do this? The message I want you to take away. So this expression for the thermodynamic entropy for the Fermi gas holds not only for the state of thermal equilibrium, it holds for any macro state. So to any macro state, yeah, so there correspond an exponentially large number of microstates, yeah, so e to the s of them, yeah, and you see there's a factor of L here. And the state of thermodynamic equilibrium is simply the one where this combinatorial factor is largest. So it's the most likely state. But there are other macrostates which correspond to exponentially many microstates. They're just exponentially fewer than the tip state, which is always the thermal one. Okay? So, some more exercises for those of you who are still keen. You can look at that later. So now, okay, in the remaining 17 minutes, I give you a crash course in Bethe-Ansatz. And obviously, I'm not going to get that far, but let me start, and then if you're interested, you can tell me, and I can tell you a little bit more in the discussion session this afternoon. So now I want to generalize what I have just told you for free theories to interacting theories. So what I need is, first of all, energy eigenstates. That's what we started with. Then we need the analog of this occupation number representation. Yeah? And I need the analogs of these particle densities, this mode occupation density n of k. That will give me the macro state. So how do I get this? And then, of course, this is just to get the macro states. Once I have this, I still need my conservation laws, you know, in order to fix the correct macro state. And that would complete the program. But let me first go through this macro state business, because that's, in a sense, just standard Bethe-Ansatz formalism. So the example I do now is the spinor-half Heisenberg chain. It's just this Hamiltonian. It's not free. It's interacting. And it's a very interesting model can be realized in cold atoms. It also is realized in many, many compounds in magnetic insulators. And it's a quantum spin chain, so spin a half on a ring of L sides, and they interact by an isotropic exchange interaction. Okay, energy eigenstates, that's very straightforward. So this is another exercise if you wish. I mean, so you know how to do this. The general form is, you just write the states in terms of product states of spins, and the factor of proportionality is just the wave function. Yeah? So this is just expanding the state in a basis, and the basis is the usual tensor product basis of spins. So states like this: up, up, down, down, up, up, down, down, dot, dot, dot. And so these product states clearly form a basis of your Hilbert space for the quantum spin chain. And these states I can always write as using these ladder operators by taking the state with all spins up and then flipping some of the spins. Yeah? And then these guys are the wave functions. So they basically tell me what is the amplitude to have down spins at positions x1, x2 to xn. Yeah? So this is obvious. Now what you do is you act with h on this. Yeah? And so you write h psi equals e psi. Time independent Schrödinger equation. Yeah? And then what you do is it's an expansion in this basis. And each term of the expansion, because these vectors here, these states are really independent, each term has to match. And that gives you the Schrödinger equation for these wave functions. And the Schrödinger equation for these wave functions just has this form here. It's not very difficult, you can just work it out. So it's some wave function. And then the interesting thing is you can solve this Schrödinger equation for n particles exactly. And this is precisely what Hans Bethe did in 1931. So if you look at the Schrödinger equation, so it has a term which is easy, which is this part. Yeah, and so just a moment. Yes, and it has a term because this basically is a piece that just amounts to spin flips hopping from one side to the next side. Yeah? And if you look at this equation for some while, you basically will realize if these positions of the downspin, so these coordinates x1 to xn, are all far away from each other. Yeah? So then the Schrödinger equation just describes a hopping model. And the hopping model you can simply describe by solve by a superposition of plane waves. Yeah? And the difficult part is when some of these downspins sit next to one another, they start interacting. Yeah? And this gives you then additional conditions. And what Bethe basically said is, well, let me make this ansatz. Yeah? I say my wave function is just a superposition of plane waves, yeah, with some momenta, which I call k1, k2 to kn. Yeah? And I basically say my wave function is a sum of all permutations of the momenta of some amplitudes times these plane waves. Substitute this in here, yeah, and it might look very difficult, it's actually not. That allows you to fix all of these amplitudes. Gives you conditions for all of these amplitudes, and you can work out what they are. So solving the Schrödinger equation gives you this expression for the amplitudes. It's expressed basically in terms of these momenta kj. All I've done here is I've changed from the momenta to some what are called rapidity variables. It's just a change of variables, because what comes next is much easier in these new variables. But so here's an explicit expression for the wave function. So I've told you what this is and what you have here. Okay, so the energies of these states are then simply given in terms of these lambda j's. Okay, And then the last thing you have to do is you have to impose boundary conditions in order to quantize the energies. So now you just impose periodic boundary conditions. So if you go around the ring, you come back to where you were. Yeah? And what that does is precisely what you expect. It quantizes the momenta. Yeah? Because now you quantize in a finite volume, so the spectrum has to become discrete. And the quantization conditions for the momenta, or these rapidity variables, are just these equations here. They're called Bethe-Ansatz equations. And now you can see how interacting integral models are very different to free ones. If you do this for a free theory, you basically just get e to the I kjl equals 1. That's the quantization condition of free theories in the finite volume. Okay, and that basically means these modes, or these are completely independent from one another, whereas in the interacting case, you see these momenta, these allowed momenta or rapidity values are correlated in a very complicated way. And that's to be expected because these spin flips, they interact in the model. Okay, and so now in order to construct macrostates, which is what we want, all we need is basically these equations. So what we want to do now is to derive the analog of occupation numbers. And to do that, we have to understand the structure of these equations. So these are a set of very complicated nonlinear algebraic equations. And of course, you can't solve them exactly. It's completely impossible. For a very small number of particles and system sizes, you can solve them numerically, but in general, it's very, very hard. Yeah. So basically what Bethe did is he reduced an exponentially hard problem to a polynomial hard problem, if you wish, but still very, very hard. Okay, so now in order to make progress, we have to understand the structure of the solution to these equations. And this we can do as follows. So we start with these equations. We want to know what is the structure of the solution. Okay, so in order to find out what is the structure of the solution, we make a simple exercise. So we take L, which is the system size large. We take the particle number small, fixed. So start with 2, 3, 4, 5, 6. And also assume that these rapidities, lambda k, which a priori are some complex numbers, are order 1. So they don't scale with system size. Yeah? So you make that assumption. And then just assume now that one of these rapidities has a positive imaginary part and see what happens. So look at the left-hand side. If lambda j has a positive imaginary part, if L is large, this becomes humongous. Very, very, very large. Okay, so basically that tells you right-hand side has to become very, very, very large. But I told you n is fixed and finite, so the only way the right-hand side can become very, very large is you have to sit on the pole of one of these factors. So there must be a lambda L such that lambda j minus lambda L is approximately equal to 2i. So I'm close to one of these poles, and then the right-hand side will be very, very large and can reproduce the left-hand side. Okay, and this consideration, now you can embellish this a little bit, be more careful, but this tells you what the structure of solution of these equations are. So they form strings. So the solution I have just described is basically a pair of rapidities, yeah, which have a spacing in the imaginary plane, which is 2i. Yeah, they're called strings because they look like pearls on a string. Okay, so now there are solutions like this. There are also longer solutions. You can have a solution where 3 of these rapidities combine to form a pattern like this. Yeah, so this is spacing 2i, this is spacing 2i. Yeah, so that's called a 3-string. And in general, you can have n of them combining in this way. Okay, so now it's clear from my discussion. So the actual solution to these equations won't have precisely the form of a string, and but instead there will be some corrections. Yeah? And these corrections can become important, yeah? In particular if you have a finite system, and if you violate any of these conditions here, these corrections can become large. But in the case we're interested in, so the thermodynamic limit at finite density and let's say a finite magnetic field, you can actually neglect these deviations. Yeah. Indeed it does. And it means that you have bound states in the problem. Yeah, and indeed, that is well known in these spin models. The elementary excitations are not just magnons or spin flips, but pairs of spin flips can form bound states, or two of them can form a bound state, or three, or four, or five, and they correspond to these string solutions. Yeah? And the spectrum in general is very complicated because as far as the integral model is concerned, all of these excitations, so the elementary spin flip or these bound states, they're all stable excitations over the ferromagnetic state.
So do these describe low energy states somehow in some sense?
They describe the excitations over the ferromagnetic state. Yeah? Because if you go back, if I could go back, I can go back. So I basically constructed my eigenstates in terms of flipping spin starting from a ferromagnet. And now if I have a finite number of lambdas, it means I have flipped a finite number of spins over the ferromagnet. I'm not really interested in that. I'm interested in a general macro state where we'll have flipped a macroscopic number. Yeah? And the excitations over that state are not at all these spin flips. They're more complicated. But I can construct them. I will actually construct them for you. Well, I mean, in the remaining 3 minutes, not. But if anybody's interested, as I said, I can tell you a little bit more. Okay, now there's a composition principle. A general solution of these Bethe-Ansatz equations with n rapidities is composed of solutions of the type I have described before. So the lambdas can be real, they can form a 2-string, a 3-string, a 4-string, and a general solution is made of these building blocks. So M1 real solutions, M2 2-strings, M3 3-strings, and so on and so forth. Then, in order to make progress, what you do now is so this classification of solution has a name. It's not exact, so we call it the string hypothesis. Yeah. But now you can use this string hypothesis. You simply say, let me just assume that I can neglect these deviations and assume strings are exact. So then you can reduce these equations to equations only for the centers of the string, because these are the only kind of non-trivial variables, because this rapidity is then related to this in a predetermined fashion. Yeah, so you can do this, and this was pioneered by Minoru Takahashi, who is one of the great heroes of Bethe-Ansatz in the 60s and 70s, and the resulting equations for the centers of the strings are, I call Takahashi's equation. After taking the logarithm of these equations, they take this form here. Yeah, so now these are the centers of the strings. So these are these quantities here. Yeah, or for a 2-string, the center of the string would be here. Yeah, the way I've written here. Oops. Okay, so these are equations that determine the centers of these strings. These functions theta and theta and m, they are known functions. They're basically just some sum over arc tangents for this XXX chain. Precise form is actually not important for the discussion here, but we always know what they are. And they are elementary functions here. And then importantly, in these equations, I get a set of integer or half-odd integer numbers, because when you take a log, you have to worry about the branch cuts of the logs, yeah, and that gives you some extra factors of 2 pi, and introduces this integer or half-odd integer numbers. And what you have to do now is you basically specify a set of these integer half-odd integer numbers. Then you solve these equations. That gives you the string centers. Yeah. Once I have the string centers, I can reconstruct the strings. And once I have the strings, I have the wave function. Yeah. So basically, the integer numbers are the good quantum numbers that completely specify the energy eigenstates. Oops. And so these are the analogs of these occupation numbers that we had in the free case. And this is what I just described. Okay. Okay. Let me see. So I think I will leave it here, because Sasha says 3 minutes. I mean, I cannot run through the remainder in 3 minutes. But basically, if I had half an hour, I could sketch for you how to. Yeah. Yeah. Okay. So basically, let me wrap it up. Yeah. So what you do now, in 3 minutes, I will wrap it up. So now microstates are characterized by these integers. Yeah? So now I want to construct macrostates. It's relatively straightforward. You go to the thermodynamic limit. The important property there is these roots, or the centers of the strings, they become dense. So the spacing between them becomes order 1 over L. And using this observation, you can turn these equations for the string centers into coupled linear integral equations for some what I call root densities, yeah, which I have defined there. But so into a set of linear integral equations for functions which I call rho particle and rho whole for each of these varieties of strings. So these equations are now called thermodynamic limit of Bethe-Ansatz equations. And each set of positive functions, now rho np and rho n whole, subject to these equations, and the fact that it gives me the correct sum rule in the thermodynamic limit defines a macrostate. So that's the macrostate. Okay, so it's a lot more difficult than in the free case. So now I need a mechanism to fix this infinite sequence of functions. Okay, and I do this once again by employing conservation laws. Okay, so what I have to do is I have to find the right conservation laws, calculate the expectation value of the conservation law in some initial state. That will give me initial data. Yeah? And then I have to calculate the expectation value of these same conservation laws in these macrostates, which are described by particle hole densities. The right-hand side is very, very easy. We know how to do this very easily. The left-hand side is the hard bit, but you can do this. And then by fulfilling all of these equations, you uniquely specify all of these infinitely many particle densities and hole densities. Yeah? And that gives you then the description of the generalized micro-canonical ensemble for the interacting case. And in the remaining 2 minutes, very briefly, what are these conservation laws? So now I look at a slightly more general Hamiltonian, where instead of 1, I put now a delta here, which I take to be larger than 1 for reasons I don't have time to explain. But so this Hamiltonian is related to a classical statistical mechanics model. So I can relate to a transfer matrix of a vertex model. The vertex model is just defined by some vertex weights. Yeah, so this is a vertex. It depends on 4 states, or which I call A, B, alpha, and beta, and each of these can take the value 1 or 2. Yeah, and the vertex model then would be something like this. This would be the partition function of some classical vertex model built from these elementary vertices. And the vertex model, as usually, you can solve by transfer matrix formalism. So you define a row-to-row transfer matrix by just picking out this part here. So that's a quantity like this. So that's a transfer matrix. We have an explicit expression for that. Integrability enters because these vertex weights fulfill the Yang-Baxter equation, which graphically can be represented like this. And from this, you can derive the fact that these transfer matrices of this classical StatMech model actually form a commuting family. And importantly, the XXZ Hamiltonian can be obtained from the transfer matrix by just taking logarithmic derivatives. So I can get the XXZ Hamiltonian from this classical StatMech model. And in fact, so can L other local conservation laws. I just take higher logarithmic derivatives. So these are my conservation laws. And because the transfer matrices commute, all of these commute, okay, then if that was the story, okay, so that would be nice. The story is actually considerably more complicated. It turns out that there are additional conservation laws because there's a much larger commuting family of transfer matrices. You get this by changing the state on this horizontal line of the transfer matrix. So instead of considering here two-dimensional space, so the index taking two values, you consider 2s plus one-dimensional space. You go through the same construction. You can construct a vertex model, and you can show that this entire family of vertex transfer matrices for this vertex model form a commuting family. And by taking logarithmic derivatives, you get more conservation laws. They're not as local as the ones I constructed first. So they basically involve interactions of spins throughout the chain, but basically the terms, which are very non-local, come with tiny exponentially small amplitudes. So these are called quasi-local. So now what you do is, so you take all of these conservation laws into account. You can calculate the expectation value in the initial state. That gives you initial data. You can calculate the expectation value in these macro states, which are described by these particle hole densities. You set it equal. That gives you the generalized micro-canonical ensemble. Once you have that, then you can go and calculate physical quantities like expectation values of local operators. And that was pretty fast. But you can ask me if you're interested the details later, and I leave it here, and thank you for your attention.
Questions?
So I presume that the last step can only be done numerically, namely that the particle hole densities to be recovered from these integrals. Well,
in general, yes. So basically, the most difficult, but there are lots of difficult steps here. I mean, let's be quite honest about it. The most difficult step is to encode the initial data, because that entails calculating the expectation value of all of these conservation laws in some quantum mechanical state. Right. And so there are tricks to make this easier. You can define appropriate generating functions for these things, which we do. But basically, it's only possible for simple initial states, which are lowly entangled. So product states or matrix product states, that you can do. And so for certain product states, you can actually do everything analytically, interestingly enough. But if you have a matrix product state, in general, it involves numerical solution of integral equations. This is true. But solving these integral equations numerically, I mean, for Bethe-Ansatz aficionados, is actually not very hard. So you can do this to very high accuracy.
General statement that if it is a product state, then you can do this analytically, or I mean, it's like the kind
of... Well, what has been done so far, the state of the art is certain classes of product states have been considered, and some matrix product states, and Well, we wrote basically an algorithm that in principle is general for matrix product states, as long as they're lowly entangled, but that involves a numerical component. Yeah, but there's a lot of scope for further developments. Let me put it like this.
Other questions? I have one naive question. So if I forget about quasi-local conservation laws and
Yes.
I try to do only with local ones, what will I miss?
You get the wrong answer. Yeah, you get the wrong answer. That's in a sense I mean, perhaps not surprising, but so basically, where does the difficulty arise? I mean, so I know where you want to go. You want to say, well, I have these, so to speak, local ones. They should be enough. Yeah. Well, the difficulty arises because we work only with thermodynamic information here. Yeah, just with the order 1 terms in the thermodynamic limit. Yeah, and so there you throw information about those ultra-local conservation laws away, and to compensate for this, you basically need these quasi-local ones. So in terms of these macro states, yeah, so these particle hole densities that specify the macro state, if I only take the ultra-local ones, I only fix the hole densities of 1 strings. And then I take the next family, yeah, which comes from a 2-dimensional auxiliary space in the vertex model. That fixes 2 strings. Then I go 3 strings, 4 strings.
So for Lieb linear model would be not a problem. You just use local.
Well, for Lieb linear, there are other problems.
Okay.
Which we can discuss.
I'll ask in private.
Yeah.
More questions? Okay, let's thank Fabian for a beautiful set of 3 lectures.